All right, we've had a look at the properties of scalar multiplication, and we've taken a look at the properties of the dot product, and those were pretty predictable. And now we're going to look at the properties of the cross product, and some of these are a little bit less predictable. There are four main four main properties that we want to talk about. The first one is something called the self-cross product. Which basically says that if you take any vector and cross it with itself, you're going to get the zero vector. Remember that the cross product results in a vector. So take any vector, cross it with itself, and you're going to get the zero vector. That's pretty easy to prove, or at least to demonstrate, by just taking any vector. Let's make it a nice generic one. Let's call it x1, x2, x3. Let's call that our vector A. And the cross product of this is going to be the I, j, k, x1, x2, x3, and then again x1, x2, x3 in a matrix. Take the determinant of this matrix, and we're going to get something times I minus something times j plus something times k. And the something I get for I results in crossing out this column and this row and taking the determinant of this matrix. I left a subscript off there. And the determinant that I'm going to get here for the determinant for this mini matrix is x2, x3 minus x3, x2. That's x2, x3. I really have got to start leaving myself more room. x2, x3 minus x3, x2. Well, these values here that are taken from this matrix, these are just real numbers. So I can do this multiplication, x2 times x3 minus x3 times x2. x3 times x2 is the same as x2 times x3. So this number here is the same as this number here. And when I subtract them, I get 0. My second component, I've already written my minus sign, is going to be x1, x3 minus x3, x1. The same thing's going to happen there. So that's going to be 0. And then the last one is x1, x2 minus x2, x1, and that's going to be 0. So even though I've used a generic a equals x1, x2, x3, those values could be anything, right? Any real number. It doesn't matter what they are. This pattern is going to pervade, and so we're going to end up with the 0 vector. So technically that's a proof because I've used a nice generic vector to do it with, but I haven't written it out as a proof, so I wouldn't really call that a proof as much as just a demonstration. But that's the self-cross product. The result of the self-cross product is that your new vector, your resulting vector, will always be the 0 vector. The second property is called the anti-commutative property. Your textbook just says anti-commutative. Anti-commutative. We've talked about this a little bit before, but we haven't been quite so specific as I'll be able to be now that we're talking about this as a property. It says that if I take the cross product of A and B and the cross product of the same two vectors but in the opposite order, it says that I'm not going to get the same thing, and we did talk briefly about that before. I'm not going to get the same result, but I am going to get a similar result. Remember that this is a vector. This will also be a vector. And the result is that if I cross in one direction, I'll get the opposite of crossing in the other direction. That's called the anti-commutative property. Property 3 is the distributive property over addition. This one just says basically that if you take the cross product of two vectors, where those two vectors are the result of vector addition and just some other vector, this cross product will be the same as if you had taken the cross product with the terms in the sum individually. So in other words, you would get something like this plus, oh, I think I want to move this. Let's put this down here. So A crossed with the sum of B and C is equal to A crossed with B plus A crossed with C. Whether you cross A with B and A with C first and then add them together, or whether you add B and C together first and then cross A with the resulting new vector that you get from addition, you'll get the same result. The fourth property is called, I don't like, this name is really weird, compatible with scalar compatible with scalar products. What this one tells us is that if I take the cross product of two vectors, that's going to be a vector, remember, and I take any real number and as a scalar, multiply it through that new vector, I'll get the same result as if I had just multiplied the first vector by that scalar multiple and then cross the result with the other vector, or scaled the second vector with that real number, that scalar, and then found the cross product of the first vector with that new scaled vector. Any three of these, whichever order you do these in, those will all return the same result. That's pretty much it. We don't need to spend a huge amount of time talking about these properties because with one or two exceptions, we've actually already talked about really some of the more important ones. I really think the most important one, or the one that'll catch you up the most easily, is this one here. That you must be careful to check the order of your cross product. A crossed with B and B crossed with A are not the same thing. This is a kind of multiplication, and we're used to, with multiplication of real numbers, we can multiply them in any order. That is not true with vectors. Vector cross products are not commutative. There is one other thing that I want to look at. Since this is a nice short video, I'm going to take just a minute and start another screen and take a look at some very specific cross products, some very important ones. You may have noticed that we've only been doing cross products on three-dimensional vectors. You cannot do cross products on two-dimensional vectors or four-dimensional vectors or anything else. A lot of the other things we've done, I've tried to give you examples in R2 and R3 and even in R4, rarely, but occasionally R5. But with cross products specifically, you can only do this. You can only do a cross product in R3. But here are some really important vectors in R3. They're I, J, and K. And by way of, let me just see if I can remind you what they are. In 3 dimensions, if I go out 1 in the x direction, I have essentially the vector 1 in the x direction, 0 in the y direction, and 0 in the z direction. In the y direction, if I do the same thing in the y direction, then I haven't moved in the x direction at all, 1 in the y direction and none in the z. And the same is true for the z standard unit vector, that's 0, 0, 1. And I want to take a look at what the cross products of some of these are. The cross product of I with J, I with K. Let me do that again. I with J and J with I, that should be two different cross products. I with K and K with I, that's two different cross products. And then J with K and J with K with J, that's two different cross products. So there's actually 6 different combinations here. I'm just going to pick one. Let's just do I and J. I crossed with J I'm going to go ahead and say I, J, K, and then I'll write the vectors out, 1, 0, 0, and 0, 0, 0, 1, 0. And I'll find the determinant of that matrix is, cross out the I column and the I row, leaving me with this matrix here. And I'll have 0 minus 0. Then I'm going to subtract something times j, and I'll add something times k. And the j comes, the coefficient of j comes about by crossing out the j's row and the j's column, which leaves me with this matrix here. I get 1 times 0, 0 times 0, so that's 0. And lastly, crossing out k's row and column, I get 1 times 1 minus 0. So here I get 1. So I crossed with j equals k. That's 0, 0, 1. And that's j. That's k. That is the k, the vector, the standard unit vector k. Let's go ahead and do one more, just for giggles, and then I think that'll be enough for you to see the pattern. Let's do j crossed with k. J crossed with k is going to be, I'm setting it up the same way. I'm using ij and k, but j is 0, 1, 0, and k is 0, 0, 1. So I'm going to get something times I minus something times j plus something times k. And I cross out I, and I get 1 times 1 minus 0. Then for j, cross out j, I get 0 minus 0. And for k, cross out the column, cross out the row, and I get 0. That gives me 1, 0, 0, and that's I. So crossing each of any pair of standard unit vectors gives you the third standard unit vector. I think that's a really interesting result. Just for fun, I'm going to do one more. I'm going to do k crossed with j, because we haven't talked about one. I'll have I, j, k for my matrix, and then I'll have k, which is 0, 0, 1, and j, which is 0, 1, 0. I need to draw a line here. And that's going to give me cross out I get 0 minus 1, and then I get, for j, I get 0, and for k, I get 0. So when I reverse the order here, these are not in alphabetical order. The same predictable thing happens here. I get -1, 0, 0, which is a scaled vector I. Ooh, that's a tight squeeze. So I get -I. I think that's a very interesting result. I don't know if you'll feel the same way, but I thought it was worth just a little bit of time on our last video for this section.